The history of warfare is littered with monuments to ambition, but few creations embody the fatal flaw of technological hubris, quite like the Panzer VIII Maus. By the later stages of World War II, as the strategic tide turned relentlessly against the Third Reich, Adolf Hitler, increasingly detached from tactical reality, sought salvation not in operational genius, but in sheer, overwhelming size. His obsession was clear: to create a land battleship, a weapon of such colossal scale and impenetrable armor that it would render all existing enemy anti-tank capabilities utterly obsolete. This political mandate gave birth to the Maus, officially designated the Panzerkampfwagen VIII, a machine that weighed a staggering 188 metric tons. To comprehend this weight is to leave the realm of conventional armor. The Maus was heavier than 2 Tiger II tanks combined, and surpassed the displacement of many small naval vessels. It was, quite literally, a fortress on tracks. The design philosophy driving this monstrous creation was fundamentally defensive and based on the principle of absolute invulnerability. Hitler mandated that the front armor must be thick enough to withstand repeated hits from the largest Allied anti-tank guns at point-blank range, a requirement that pushed the front glacis plate to an almost unbelievable 220 millimeters of hardened steel. The tank's main turret, a squat massive cylinder, was armed with dual high-caliber cannons, the 128 mm KWK 44L55 and a coaxial 75 mm KWK 44L36, capable of engaging and destroying any known Allied armor at extreme range. The entire machine was a physical manifestation of Hitler's belief that superior armor and firepower could compensate for the collapsing tactical and numerical reality facing the Wehrmacht. The project was handed to 2 of Germany's foremost industrial minds: Professor Ferdinand Porsche, renowned for his unconventional electric drive systems, and the heavy industry giant Krupp, tasked with forging the massive steel components. From the beginning, the sheer scale of the project presented an array of near insurmountable engineering challenges, the most critical of which lay not in the armor plating, but in the power plant itself. The vehicle required an engine and transmission system capable of moving this 188-ton behemoth across varied terrain at a useful combat speed, a requirement that defied the existing limits of contemporary engine technology. The decision to use a complex gasoline-electric drive system was a direct consequence of the immense weight. No conventional mechanical transmission could handle the colossal torque required to propel the Maus. The forces involved would simply strip the gears instantly. Thus, the engineering pivoted to a locomotive-style system, where an internal combustion engine would function primarily as a generator, feeding electrical power to individual traction motors located near the drive sprockets. This theoretically robust solution was the chosen path to moving the immovable object. However, the available engines, initially based on a modified Daimler-Benz aircraft engine, were critically underpowered for the task. The resulting failure was mechanical and systemic. The massive tank, designed to be an unstoppable weapon, literally consumed its own engine power, moving at speeds so glacial and demanding so much internal energy that it became a logistical and operational absurdity. The Panzer VIII Maus was not defeated by Allied artillery. It was ultimately defeated by the unyielding laws of physics and the sheer inadequacy of its own mechanical heart. The engine room of the Maus was the epicenter of its catastrophic failure, a complex space where engineering ambition collided violently with industrial limitation. The primary power challenge was to achieve a useful power-to-weight ratio. The colossal 108-ton chassis demanded an output of power that simply did not exist in any reliably mass-produced German engine. The initial chosen solution was a modified Daimler-Benz DB603 V12 aircraft engine, later swapped for a Daimler-Benz MB509, a derivative of the DB603 designed for tanks. This engine, capable of generating around 1,080 horsepower, was formidable by conventional tank standards. But when mated to the 188-ton chassis, The resulting power-to-weight ratio was a pitiful 5.7 horsepower per ton. To put this into perspective, the highly successful Panther tank enjoyed a power-to-weight ratio of approximately 15 horsepower per ton, giving it superior speed and agility. The Maus, therefore, moved at a crawling pace, barely managing speeds of 13 kilometers per hour, 8 mph, on flat, level ground, and suffering dramatic performance decay on any incline or soft terrain. Professor Porsche's team selected the gasoline-electric drive system precisely because conventional transmissions, with their complex gear linkages, would fail under the tremendous load generated by the colossal weight of the vehicle. The electric drive offered superior torque characteristics and flexibility. The MB509 engine powered a primary generator, which in turn provided electricity to 2 electric motors, one driving each track. While robust in theory, the constant mechanical demand placed on the engine, running at near maximum output simply to achieve minimal road speed, resulted in extreme stress and premature wear. The engine was essentially forced to operate at its absolute limit continuously, leading to chronic overheating, excessive fuel consumption, and rapid component degradation. The tank, unable to move without maximum exertion from its power plant, was literally consuming the lifespan of its own engine simply to propel itself across the landscape. The need for specialized, high-capacity cooling systems, massive radiators, and complex air intake systems to feed the engine and generator further compounded the tank's size and logistical burden. The engine room became a thermodynamic nightmare, a place where immense heat generation threatened to degrade the sensitive electrical components of the drive system itself. The failure of the Maus was, fundamentally, a failure of propulsion. A massive tank chassis was engineered for absolute defense, but its mechanical heart was critically insufficient for the impossible task of moving its own body, dooming it to be a slow, heavy target rather than the mobile fortress Hitler envisioned. The challenge of powering the Panzer VIII Maus was intricately linked to the immense logistical absurdity of the vehicle's weight. At 188 metric tons, the Maus immediately rendered nearly all existing European infrastructure irrelevant. The tank's crushing weight exceeded the certified load limits of virtually every road bridge in Europe. This logistical constraint fundamentally crippled the Maus's operational doctrine, preventing it from functioning as a true offensive weapon capable of rapid deployment or crossing key river crossings. The only possible solution devised by the engineering team was equally absurd. The Maus would have to bypass all bridges and ford rivers completely submerged. To achieve this impossible feat, the tank was designed with a complex deep wading system, which included massive internal air tanks and a sealed hull capable of operating completely underwater. This required the tank to be fully submerged, driving along the riverbed, guided only by a towering snorkel mast that extended above the water's surface to provide air for the crew. The technical demands of this deep wading system were enormous. Every seal, every hatch, and every vulnerable access point had to be meticulously engineered for absolute watertight integrity to withstand the crushing hydrostatic pressure of being submerged. Furthermore, the electronic drive motors and critical battery banks had to be perfectly insulated and protected from water ingress. A massive technical challenge given the complexity of the internal wiring and hydraulics. Even if the tank could successfully ford a river, the sheer time and resources required to prepare the vessel for submersion, sealing the hull, setting up the snorkel, coordinating the operation, made rapid movement across broken terrain impossible. The necessity of this complex deep wading system underscored the critical engineering failure. Instead of designing a tank that could operate within the existing logistical landscape, the engineers designed a weapon that demanded the landscape be physically remade around it. The operational reality was that the Maus would either have to drive hundreds of miles out of its way to find terrain free of river crossings, or it would require massive, specialized bridge-laying equipment, which of course did not exist, to move across the theater. The weight of the Maus was its own greatest enemy. turning every small stream and every standard road bridge into an impassable obstacle, sealing its fate as a static, defensive asset rather than the mobile, armored breakthrough weapon Hitler demanded. The extreme scale of the Maus not only crippled its propulsion, but also created profound manufacturing and material allocation crises within the strained German war economy. The sheer quantity of specialized steel required for the 220mm front armor and the massive turret was astronomical. Each Maus hull consumed resources that could have been used to produce several standard Panther or Tiger tanks, leading to significant internal debate and resentment within the German armaments industry. The project became a sinkhole for Germany's dwindling specialized material reserves. Krupp, the firm primarily responsible for casting the massive armor components, faced unprecedented challenges. Forging and machining the colossal armor plates, especially the turret shell, required specialized facilities, unique heating processes, and prolonged cooling times to ensure the structural integrity of the steel. The manufacturing process was slow, complex, and highly vulnerable to interruption from Allied bombing. The immense size of the components also created catastrophic challenges for internal logistics within the factories and for external transport. Moving the 50-ton turret components and the massive assembled hull sections required specialized rail cars and reinforced tracks, infrastructure that was already buckling under the strain of continuous wartime transport. The construction of the test chassis itself consumed crucial resources. By the end of the program, only 2 prototypes were partially completed, 1 hull and 1 turret, designated V1 and V2, a fraction of the original order. The production timeline was continuously delayed by the complexity of the components, the lack of powerful enough specialized welding equipment, and the constant diversion of priority resources to immediate, pressing defensive needs, such as anti-aircraft guns and standard tank production. The structural flaw of the Maus was therefore not just mechanical, but systemic. It was a weapon engineered for a scale of industrial production that the collapsing Third Reich simply could no longer support. The economic absurdity of the tank's weight ensured that it remained a theoretical curiosity rather than a practical instrument of war. The entire project served as a prime example of the disconnect between Hitler's ambitious fantasies and the brutal, diminishing reality of Germany's industrial capacity. Professor Ferdinand Porsche's choice of the gasoline-electric drive system was a necessary engineering workaround, but it introduced a new layer of complexity and vulnerability into the already strained mechanical structure of the Maus. The system, while avoiding the catastrophic failure of a mechanical transmission under the 188-ton load, forced the internal combustion engine to operate continuously as a high-output generator. The engine, initially based on the DB603 aircraft design, was ill-suited for the prolonged, high-stress demands of land transport. Aircraft engines are designed for high-altitude, short-burst performance, not for continuous, ground-level, heavy-load operation. The constant, near-maximum output required simply to move the tank across open terrain led to chronic and extreme thermal stress. The engine room became a thermodynamic nightmare. The heat generated by the massive engine and the primary generator threatened to degrade the sensitive electrical components of the traction motors and the complex wiring harness. The cooling system, which included massive radiators, fans, and complex internal plumbing, had to be disproportionately large and heavy, further adding to the overall mass of the tank. Despite these massive cooling efforts, overheating remained a persistent, critical problem, threatening the longevity of the entire power plant. Furthermore, the electric motors themselves, while offering superior torque, added significant weight and complexity. The energy conversion from gasoline to electricity and then back to mechanical traction was inherently inefficient, consuming fuel at an astronomical rate and reducing the operational range. The Maus was designed for long-range offensive breakthroughs, yet its fuel consumption severely restricted its tactical utility. The power plant of the Maus, therefore, became a complex, fragile, and energy-intensive system that consumed itself in the simple act of motion. The initial engineering choice, intended to solve the immediate problem of weight, created a cascade of thermal and efficiency problems that the German wartime industry could never reliably solve, cementing the tank's reputation as a slow, unreliable logistical white elephant. The operational deployment model for the Maus was dictated entirely by its crippling weight and lack of mobility. Initially conceived as a mobile armored breakthrough weapon, its logistical limitations soon forced the military command to reconsider its role as a static, defensive asset, a massive, movable bunker. The plan involved deploying the few anticipated Maus tanks to critical defensive sectors, such as coastal defenses or key river crossings, where their absolute invulnerability could be maximized. Their role would be to act as mobile shields, anchoring the line against any potential massive Allied armored push. This shift in doctrine, however, exposed a different kind of failure. A defensive weapon of the Maus's size requires immense logistical support that was simply unavailable in the late war environment. Transporting the 188-ton behemoth, even over short distances, required specialized, heavy-duty rail transport, infrastructure that was constantly targeted by Allied air superiority and already buckling under the strain of supplying the Eastern Front. Furthermore, even if the tank could be successfully moved to a deployment area, it required an astronomical volume of fuel, specialized maintenance crews, and a robust supply chain to keep its complex electric drive operational. The infrastructure needed to support a single Maus tank could have serviced an entire battalion of smaller, more mobile tanks. The paradox was complete. The tank designed for absolute invulnerability was rendered operationally useless by the very weight that was supposed to guarantee its survival. The strategic value of a highly visible, static defensive asset was negligible compared to the colossal drain on the collapsing German economy. The Maus, therefore, remained a political symbol rather than a tactical reality, a static monument to Hitler's increasingly desperate fantasies of an invincible weapon that could defy the diminishing reality of the Third Reich's industrial and military capabilities. Its operational doctrine was fundamentally flawed, dictated by a weight that demanded logistical miracles impossible to achieve under continuous Allied pressure. The challenge of moving the Maus from the factory floors of Krupp and the assembly lines of Alkit to the front lines required engineering logistics that were utterly divorced from wartime reality. Transporting the assembled tank was deemed impossible by standard rail networks due to its weight and the immense width of the tracks, 1.1 meters wide. The initial solution was to disassemble the tank into its primary components, hull, turret, and running gear, and transport them on multiple specialized rail cars. However, even the single 50-ton turret component required massive cranes and reinforced rail lines, consuming precious time and resources. The assembly process at the final deployment location was equally prohibitive, requiring massive machinery and several weeks of dedicated labor, time the Wehrmacht could never afford during a fluid crisis. The final proposed solution was the development of specialized, oversized railway transport wagons with multiple axles designed to distribute the immense weight. Yet, these wagons themselves required massive steel resources and were highly vulnerable to air attack, making the transport operation a significant risk. The logistical absurdity was best illustrated by the recurring problem of river crossings. The only viable solution remained the deep wading system, requiring the tank to be fully sealed and driven across riverbeds submerged. This complicated procedure demanded specialized external electrical connections to a second Maus unit, which would ferry power across the water to the submerged tank, and meticulous preparation of the entry and exit points of the riverbank. This complex process effectively eliminated any possibility of rapid, tactical maneuver. The logistical demands of the Maus highlighted a critical operational flaw. The tank was not designed for the war being fought. It was designed for an imaginary industrial state with unlimited resources and absolute control over its transport infrastructure. The reality of continuous bombing, disrupted rail networks, and a critical shortage of fuel meant that the Maus remained trapped in the supply chain, consuming resources but unable to deliver its promised invincible firepower to the decisive points of conflict. The immense firepower of the Maus, centered on the colossal 128mm KWK-44L55 gun, was intended to secure its tactical superiority, but the sheer size of the armament created a new series of engineering and operational paradoxes. The 128mm gun was capable of destroying any Allied tank at extreme range, a formidable deterrent. The secondary coaxial 75mm KWK-44L36 gun provided versatile defense against lighter targets and infantry. However, mounting this massive gun system required a turret that weighed over 50 tons and demanded specialized electrical traverse mechanisms, as manual rotation of the massive turret ring was impossible. The weight and complexity of the turret assembly placed extreme stress on the already inadequate propulsion system. Moving the turret, aiming the guns, and simultaneously propelling the chassis placed an insurmountable load on the generator and electric motors. Furthermore, the immense size of the 128mm shells required a massive internal storage capacity and a complex loading mechanism. The high-caliber ammunition was itself heavy and consumed vast amounts of specialized components and propellant. The rate of fire for the 128mm main gun was inherently slow due to the size of the projectiles and the necessary loading procedures. The combined armament package, while theoretically devastating, contributed significantly to the tank's logistical absurdity and mechanical strain. The paradox of the armament was complete. The guns were designed for long-range offensive breakthrough. Yet the tank was restricted by its own weight to a static, defensive role. The immense power was unusable in a fluid, rapidly changing battlefield environment. The ultimate AAR conclusion on the Maus's armament is that the scale of the guns was dictated by political ambition rather than practical tactical necessity. The tank was overgunned and over-armored for the war being fought, consuming resources that could have been used to equip numerous standard tanks with effective, if less intimidating, firepower. The final chapter of the Maus's development was characterized by a frantic, often chaotic testing regime that consistently exposed the tank's crippling performance flaws. Testing focused initially on the prototype V1 chassis, without the operational turret, emphasizing mobility and propulsion integrity. These tests, conducted on specialized proving grounds, confirmed the worst fears of the engineers. The 188-ton tank was agonizingly slow, suffered from massive fuel consumption, and experienced chronic mechanical failures due to the stress placed on the engine and suspension. The specialized suspension system, comprised of complex bogie assemblies designed to distribute the colossal weight, was prone to rapid wear and required constant maintenance. The tracks themselves, 1.1 meters wide, exerted immense pressure on the ground, limiting the tank's operational terrain to hard, flat ground. Any soft ground or deep mud rendered the Maus immobile, risking complete immobilization on the battlefield. Despite these persistent failures, the political mandate from Hitler forced the continued development of the V2 prototype, which included the fully assembled turret. The addition of the 50-ton turret further exacerbated the performance issues, reducing the maximum speed and placing even greater thermal stress on the engine and generator. The testing revealed that the vehicle's turning radius was immense, making tactical maneuvers in close-quarters urban or forested environments practically impossible. The Maus required huge, open spaces to operate effectively, a logistical luxury that the Wehrmacht no longer possessed in late 1944. The test data provided a clear, undeniable verdict. The Maus was a strategic liability. Its weight ensured logistical paralysis, its propulsion was unreliable, and its mobility was insufficient for modern warfare. The tank was a museum piece before it ever left the proving grounds, a testament to the fact that absolute scale does not guarantee battlefield effectiveness. The decision to continue the project, consuming crucial resources until the final days of the war, highlighted the complete disconnect between the political leadership's fantasies and the grim engineering reality. The ultimate political and strategic failure of the Maus was its role as a monumental resource sink in the collapsing German economy. The project consumed specialized steel, unique electrical components, and thousands of skilled man-hours that were desperately needed for the immediate defense of the Reich. The resources allocated to the handful of Maus prototypes and their associated infrastructure could have produced hundreds of highly effective Panther or Jagdpanther tanks, which were proven operational assets. The political decision to prioritize the Maus, a tank guaranteed to be unreliable, immobile, and strategically irrelevant, over the mass production of proven designs, was a direct consequence of Hitler's increasing fascination with Wunderwaffen, wonder weapons, and his belief in technological infallibility. The continuous bombing campaign by the Allies amplified this resource drain. The complex manufacturing processes were repeatedly interrupted, leading to costly delays and rework, further consuming resources. The commitment to the Maus reflected a fundamental flaw in the German strategic command, a failure to adapt to the reality of the war of attrition. Instead of maximizing the efficiency of existing, proven designs, the command chased extravagant, high-risk projects that offered theoretical invincibility but delivered operational failure. The legacy of the Maus is not just its mechanical inadequacy, but its profound strategic failure to adapt to the diminishing reality of the war. It stands as a physical symbol of the Third Reich's final, desperate, and irrational attempt to reverse the tide of the war through sheer, brute force engineering. The tank that was intended to be the ultimate weapon against the Allies was ultimately defeated by the unyielding economic and logistical laws of physics. The design and political imperative behind the Maus ultimately reflected Hitler's personal strategy of total defense rather than effective offensive maneuver. The focus on 220 mm of front armor was driven by the desire to create a vehicle that was literally invulnerable to any known Allied weapon at any range. This singular obsession with static defense dictated the entire design philosophy, leading to the crippling weight. The tank was not intended for flanking maneuvers, rapid deployment, or exploitation of breakthroughs, all critical elements of mobile warfare. Instead, it was conceived as a mobile pillbox, designed to anchor a defensive line and absorb catastrophic amounts of enemy fire. This emphasis on defense revealed a fundamental misunderstanding of the nature of modern mechanized warfare, which prioritizes mobility and rapid response over impenetrable, slow-moving armor. The ultimate expression of this defensive mindset was the tank's logistical failure. The inability to cross bridges or travel over soft terrain meant that the Maus could only be deployed to predetermined, heavily surveyed defensive positions. The tactical reality was that any weapon confined to such predictable positions is easily circumvented. The colossal resources poured into the armor plating were effectively wasted, as the tank's mobility ensured it would never truly face the concentrated fire required to test its invulnerability. The Maus, therefore, became a tragic manifestation of a defensive mindset, a machine built to withstand a siege but incapable of fighting a war of movement. The final bizarre chapter of the Maus program was its intended role in the defense of Berlin. Although only 2 prototypes were ever partially completed, the political significance of the tank was immense. As the Soviet armies closed in on the German capital in 1945, the remaining prototype hulls and components were ordered to be defended at all costs, potentially to be used as static defensive batteries. The hope was that the sheer presence of the 188-ton monster, even if immobile, would serve as a psychological deterrent. The reality was far grimmer. The two partially completed prototypes were ultimately destroyed by their own crews near the Kummersdorf proving ground to prevent their capture by the advancing Soviets. The only surviving vehicle today is a composite of the V-1 hull and the V-2 turret, assembled by the Soviets after the war. This final act of self-destruction confirmed the tank's ultimate operational failure. A vehicle built to be absolutely invincible was never used in battle and was destroyed by its own creators. The technical reasons for the destruction were sound. The logistics of evacuating a 188-ton vehicle under fire were impossible, and the secrets of its electric drive system were too valuable to be compromised. The surviving composite Maus now rests in the Kubinka Tank Museum in Russia, a permanent physical testament to the irrational overreach of the Third Reich's Wunderwaffen program, and the absolute failure of a tank that prioritized scale over combat reality. The analysis of the Maus's suspension system further exemplifies the extreme engineering challenges imposed by Hitler's weight mandate. The tank required a specialized, complex suspension capable of absorbing and distributing the crushing 108-ton load across its 1.1-meter wide tracks. Porsche's team developed a unique bogie assembly system featuring multiple road wheels paired on torsion bars. This design was technologically sophisticated and essential for the task, but it was incredibly complex to manufacture, assemble, and maintain. The constant, massive load placed on these components led to chronic problems with rapid wear and metal fatigue. The specialized materials and precision required for the suspension components were constantly being diverted to more pressing war needs, further compromising the reliability of the system. The suspension system, much like the engine, was constantly operating at its structural limit. Any small bump or terrain irregularity transmitted enormous shock forces throughout the chassis, threatening the integrity of the tracks and the sensitive components of the electric drive. The necessity of this complex and fragile suspension system underscored the fundamental flaw of the Maus. Every component, from the engine to the tracks, had to be disproportionately heavy and complicated simply to manage the vehicle's own mass, diverting resources from the front line and ensuring continuous mechanical vulnerability. The final, critical lesson offered by the Panzer VIII Maus is a stark reminder of the limitations of centralized political authority in military engineering. The tank's existence was not justified by military necessity or battlefield doctrine. It was a direct product of the personal, unshakable fantasy of Adolf Hitler. The design parameters, the extreme armor thickness, and the colossal weight were mandated by political fiat, overriding the pragmatic concerns of engineers like Speer and even the operational commanders. This centralization of design authority led to a catastrophic misallocation of national resources and forced brilliant engineers like Porsche to pursue technologically absurd solutions. The decision to continue the Maus program, consuming vast resources throughout 1944 and 1945, when Germany desperately needed thousands of small, reliable tanks and anti-aircraft guns, highlights the ultimate irrationality of the Nazi regime's Wunderwaffen obsession. The project became an expensive distraction, diverting skilled labor and specialized materials from proven, effective weapon systems. The Maus, therefore, serves as a historical case study in the perils of allowing ego and political fantasy to supersede the objective realities of engineering and logistics. The consequences were clear: the creation of a massive, immobile monument to ambition that was incapable of fulfilling its basic mission. The final after-action report on the Panzer VIII Maus offers a conclusive verdict on the ultimate failure of scale in warfare. The tank that was intended to be absolutely invincible was instead defeated by the simple physics of weight, friction, and power consumption. The project was an economic and logistical tragedy that consumed resources far out of proportion to its military value. Its core mechanical failure, the inability of the gasoline-electric drive system to reliably propel and cool itself, doomed the tank before it ever faced an Allied gun. The legacy of the Maus is not one of terrifying power, but one of cautionary overreach. It is a permanent physical symbol of the dangers of technological hubris, demonstrating that sheer size and invulnerability cannot compensate for a lack of mobility, reliability, and logistical feasibility. The lessons learned from the disastrous engineering efforts on the Maus ultimately guided post-war tank design, reinforcing the doctrine that a tank's effectiveness is defined by its optimal balance of protection, firepower, and, most critically, mobility. The Panzer VIII Maus failed its war, not on the battlefield, but in the engine room, a static monument to the unyielding laws of physics that even the most determined dictator could not overcome.